Wouldn't life be easier if we could exist in multiple places at once? What if I told you that the Copenhagen interpretation of quantum mechanics allows you to do that? Well, I'd be lying. Because it doesn't allow you to do that, but it does allow your particles to exist in multiple places at once, and while that isn't necessarily as helpful, it's pretty fascinating. When I was little, my friends and I used to play a game called Wall Touch. In it, I would stand facing a wall, and my friends would line up behind me. Their objective was to come and touch me on the back, but every time I turned around, they had to freeze. When I wasn't looking, they could have been at any distance away from me, but when I turned around, they were forced to choose a position, and that's kind of how the Copenhagen interpretation works. The act of observing subatomic particles forces them to choose a state. But there's a couple issues with my analogy. For one, when I'm not looking, my friends are at some distance from me, I just don't know what that distance is. But when we aren't observing subatomic particles, they are in all possible states at once. If my analogy was accurate, that's as if my friends were at all distances away from me and on the other end of the galaxy, which is an unfair advantage. If you'll notice, I said states and not positions. That's because under Heisenberg's uncertainty principle, we're talking about both a particle's position and its momentum. When I turn around, my friends stop, and I know both their position and their momentum with complete certainty. But when we observe subatomic particles, it's not that they stop moving, it's that they choose a state of both some position and some momentum. But under the laws of quantum mechanics, we either know one or the other with complete certainty, but never both. So then how do we know that the particles that make us up would be here and not somewhere else if we were to observe them? Well, we don't really. But what we do know is that there's a probability of them being one place as opposed to another. This probability is given to us by Schrödinger's equation. H bar represents the scale of this stuff, and it's really tiny, which is why your particles exist in multiple places at once, but you don't. This is a partial time derivative, and it tells us that the probability changes over time. The longer I'm looking away, the higher the probability that my friends are closer to me. And this is the Hamiltonian, and it describes the state of the system. You can think of this as my friend's athleticism. Just as athleticism doesn't look the same from person A to person B, the Hamiltonian differs from particle to particle. And this is psi, and physicists don't really know what it is. But its square gives us the probability wave that tells us the locations of subatomic particles. And you can think of this as my friend's ambition, because it's influenced by all these other factors, but it's key in determining their success, which in this game is their location. All of this can be really disconcerting, and in fact some of the earlier physicists didn't want to believe in it at all. But I take some solace in the fact that when I'm feeling all over the place, it's because my particles kind of are. So to bring Niels Bohr and Marie Antoinette together, let God play dice.